Hi everyone. In this video, we'll be discussing indefinite integrals and the method of U-substitution. In particular, in this video, we will define an indefinite integral of a function. We'll use our knowledge of the chain rule to find antiderivatives of certain functions, and we'll observe how substitution can be used to simplify more complex antiderivatives. So let's first begin with the definition of an indefinite integral. Suppose f is a continuous function for x values between a and b. Then the indefinite integral of that function f on the interval a to b is the collection of all antiderivatives of the function little f. Namely, we say the indefinite integral of f of x is equal to capital F of x, where capital F of x is some antiderivative of little f of x, plus some constant c. So really what we're doing here is we're just defining an indefinite integral. We already defined a definite integral where you might have, for example, limits of integration here and here. That's a definite integral, but now we're defining an indefinite integral, which is just the collection of all possible antiderivatives. So you take one antiderivative, capital F of x, and then any other antiderivative must be that function plus or minus some constant. We just write plus here because we're assuming that constant c could be any real number, positive or negative. So in simple cases, indefinite integrals can be found directly. So for example, I may recall from Calculus 1 that the derivative of arctangent or tangent inverse of x is 1 over 1 plus x squared. So since I know that the derivative of tangent inverse of x is equal to 1 over 1 plus x squared, then that immediately tells me that the indefinite integral of 1 over 1 plus x squared is an antiderivative of that. Well, an antiderivative of 1 over 1 plus x squared is tangent inverse plus c. Okay. So the plus c, maybe it seems sort of trivial, right? But really what we're expressing is that there are many possible antiderivatives, and they can all be characterized as tangent inverse of x plus or minus some constant. Okay. So in simple cases where we may be able to look at something and know an antiderivative just from our rules for differentiation, we can find indefinite integrals. It's really the same as finding an antiderivative in some sense. It's just asking a slightly different question. If I ask you for a antiderivative, then you could just give me tangent inverse of x. If I ask you to find the indefinite integral, then I'm asking you to find all antiderivatives. So it's really just tangent inverse of x plus some constant. All right, let's move then to maybe a slightly more challenging problem. So if I look at this, I don't immediately know some differentiation rule that tells me that if I take the derivative of some function, I get this, right? So I need to work a little bit harder. And if I sort of stare at the integrand for a minute, so for example, right, this is what we refer to as our integrand, the thing we're integrating. Okay. If I look at that, it's a product of things, and it sort of looks like the kind of thing that might come out of doing a chain rule. So if I look at that for a minute, I might sort of play around with it, and I might wonder, okay, well, what is the derivative of sine of x cubed? So to find the derivative of sine of x cubed, I need to apply the chain rule because I have a composition of functions. So I have sine of something, and that something here is x cubed. So in applying the chain rule, I take the derivative of the sine function and evaluate it at x cubed. So the derivative of the sine function is cosine. So I'll get cosine of x cubed. But then I get times the derivative of this inside function x cubed, and its derivative is 3x squared. And so, in fact, the derivative of this is 3x squared times cosine of x cubed. Now, having made that observation that the derivative of sine of x cubed is 3x squared cosine of x cubed, which is our integrand, then I now know that sine of x cubed is an antiderivative of 3x squared cosine of x cubed. So up here now I can say, okay, well then I know that this ought to be equal to sine of x cubed plus c, right? Plus any constant c you want to put there. So in this case, I was able to do this, but only because I sort of looked at it and I thought, well, maybe that came from a chain rule, and if that came from a chain rule, then maybe I could sort of guess around here into what might have given me this as a derivative, right? In general, though, that could be quite tricky, right? To look at something and immediately see that, oh, that thing actually came out of doing a chain rule. And then even if you could recognize that, trying to sort of reverse engineer the right function here that will give you the derivative, which is your integrand, that's sort of hard to do if you're just sort of trying to stare at it and hope an answer occurs to you. So what we wanted to come up with is a more systematic approach for solving these sorts of problems. And this is going to be what we're going to call the method of U-substitution. So to see why the method of U-substitution works, let's sort of imagine, right? We want to sort of think about the fact that we're integrating something that came out of doing a chain rule. So I want to imagine that I see something that looks like f of g of x, and then over here I see g prime of x. Now, you might be thinking that normally that's not how you see the chain rule. Normally, what you see here, if this were going to be from the chain rule, would be something like f prime of g of x times g prime of x. But little f is really capital F prime. So this is really capital F prime of g of x times g prime of x. And so this comes from taking the derivative of capital F of g of x. Okay, so by the chain rule, what we really get here is that this is the derivative of this, or said another way, this is an antiderivative of this. Okay, and so from the chain rule, we get this. Okay, but again, it's sort of maybe hard to see how that would necessarily work if you were just, I don't know, just staring at this with some functions. So we want to think about this in a slightly different way. Okay. So I want to think about making a substitution here. So this is what we're going to call our U-substitution. So I'm going to let U be equal to g of x. And if I do that, then du dx would be g prime of x. Now, over here on the right-hand side, if I just substitute in, right, this is capital F of u plus c. And that really, what is that? That's just the antiderivative of little f with u plugged into it. So this is really, I could also write this as the indefinite integral of little f of u du, right? This is just what you get when you take the antiderivative of little f and you plug in u. Okay. Now, if I look at the left-hand side, I have this piece sitting right here, okay? And if I were to just substitute in here, switch pens here, I would get over here the integral of f of u times du dx dx. So now let's see, this seems sort of like just a bunch of manipulation. So let's see if we can understand what this is really telling us then. What this is saying is, if I see an integral that looks like the integral of some function of another function. So I'm thinking of u, right? It's really like that g of x, right? And then I see the derivative of that inside function sitting in the integrand also, then I can actually just rewrite this as the integral of f of u du. Okay. So, for example, going back to the previous case, right, we had the integral of 3x squared cosine of x cubed dx. Here is, oh, sorry. Here is my u, and here is du dx. So what I have is f of u times du dx. And what this says is that if I want to do that, that's really the same as just integrating cosine of u du. Well, I know the antiderivative of cosine, that's just sine of u plus c. And now if I just remember what u is, well, my u here was x cubed. And so plugging that back in, I would just get sine of x cubed plus c. Sorry, that actually cut off a bit there on the bottom. So maybe I'll just show you, right? I can just plug this in here, right? And I get sine of x cubed plus c. So this is sort of the theoretical framework for how this all works. But again, we want maybe a slightly more algorithmic approach to solve these quickly. And so let's formalize then the method of U-substitution based on these observations. All right. So the first thing we're going to do for the method of U-substitution is we're going to look at our integrand and we're going to try to identify some function u and its derivative both sitting inside of our integrand. We're going to look at several examples as we practice this, but we're going to first try to identify a function and its derivative sitting inside our integrand. We're going to call that function u. Its derivative obviously would be du dx. Or in the case that you're integrating with respect to some other variable, du d that variable, right? So it could be du dt, du d theta. We'll see some other examples as we go, but a function and its derivative sitting inside the integrand. Once we've identified those, then we're going to rename them. So we're going to replace that function with u, and we're going to replace its derivative with du dx in your integrand until the integral now only depends on u. Now, in order to do this, we're going to take advantage of that formula we just wrote down. So we're going to say, okay, I have f of u times du dx dx, and that's equal to the integral of f of u du. Now, what we're going to do as sort of a bit of sleight of hand often is we'll just sort of pretend like we're canceling these. Now, mathematically, that makes no sense. Du dx is not a fraction. The dx here, these things don't represent real numbers. So we can't treat them like fractions and real numbers and use properties of cancellation for fractions. However, this equality that we just derived earlier, right, shows us that if we want to think about it that way, that's fine because it is in fact equal to this. Okay, so we'll do a bit of sleight of hand there to sort of make our lives a little bit easier. And then once we've done that, hopefully we'll end up with an integral that's easier to evaluate. So in step 3, we'll just evaluate the integral. And then once we evaluate that indefinite integral, we'll undo the substitution by plugging back in whatever u was set equal to at the beginning so that we get our answer back in terms of our original variable. To really see how this works, let's look at a couple of examples. Okay. So let's start here. We have the integral of 4x cubed times the square root of x to the 4th plus 5. Okay, so step 1 is to identify a function and its derivative sitting inside of this problem. So as I look at this, and in particular, anytime I have sort of polynomials floating around, right, I see something like an x to the 4th and something like a 4x cubed. Okay. So one thing I could do is I could select my u to be x to the 4th, and then my du dx would be 4x cubed. However, I often want to make my u as large as possible. And notice that if I set u to be equal to x to the 4th plus 5, I'll still get my du dx to be 4x cubed. So substituting those values into my indefinite integral, what do I get? Well, the 4x cubed is going to be replaced by du dx. And then instead of square root of x to the fourth plus 5, I'm going to have square root of u and then dx. And now this is where I can do sort of some sleight of hand. This is square root of u, du dx, dx. So this ought to be the same as the indefinite integral of the square root of u du. And, well, square root of u, that's really just u to the 1/2 du. Now, because this is written as just a power of u, this is a fairly straightforward integral to take. So we're going to increase the power by 1 and divide by the new power to get an antiderivative. Okay, so if I increase that power by 1, I'll get that is u to the 3/2 divided by 3/2 plus c. Simplifying that a bit, that's 2u to the 3/2 over 3 plus c. And then finally, in my last step, I need to identify or what my u was originally and convert my answer back in terms of my original variable. So u was actually x to the fourth plus 5. So my final answer should be 2 x to the fourth plus 5 to the 3/2 over 3 plus c. And so this is my final answer. Now again, let's sort of review the steps. First, we identified a function and its derivative sitting inside of our integrand. Okay. By making then that substitution, okay, we were able to reduce our integral to be something that was only in terms of u. If there are x's still floating around, and we'll sort of see how that could happen later, then we haven't made a valid substitution. But in this case, because I've reduced everything to being in terms of u, this is a good substitution. Now notice that this antiderivative is much easier to find than this antiderivative. That's the whole point of U-substitution. Okay. And so now I can find an antiderivative of this function. Okay, and so that was just u to the 3/2 divided by 3/2, which I simplified here. And then in my final step, I just need to take this u and remember that u was actually just a placeholder for x to the fourth plus 5. So everywhere I see u now, I plug in x to the fourth plus 5 to get my final answer. All right, let's look at another example. All right, so here we have sine to the 5th of 2x times cosine of 2x. So here I see some trig functions floating around, but I have this sine to the 5th power. It might be helpful to remember, right, that sine to the 5th of 2x is the same as sine of 2x, whole thing raised to the 5th power. Okay, so I could just come over here and remind myself that this is really the same as the integral of sine of 2x to the 5th times cosine of 2x dx. And so if I'm looking at this, I probably think, well, okay, I see a sine and I see a cosine. They're both sort of derivatives of one another. The problem I might be worried about, though, is that the derivative of sine of 2x is not cosine of 2x. The derivative of sine of 2x is 2 cosine of 2x. So I don't see quite its derivative sitting here, but it's very close. It's the derivative, but it's just the constant that's multiplied by out in front is sort of not quite right. Okay, so let's see though what we could do. So what if I let u be equal to sine of 2x? Okay, then what would du dx be equal to? Well, du dx, we just said, would be 2 cosine of 2x. Now, of course, the problem that I have here, right, is that I could put u in here, but what am I going to do with this? Well, I have a cosine of 2x, not a 2 cosine of 2x. But what if I took this 2 and moved it to the other side? So I could divide both sides by 2. And so now where I have this cosine of 2x, I could substitute in 1/2 du dx. And so if I were to make that substitution, I would get that this is equal to the integral of u to the 5th. So my u is sine of 2x, so this becomes u to the 5th times 1/2 du dx dx. So now if I look at this, okay, I have this constant 1/2, it can come out front. The dx's will cancel here. This will become 1/2 integral u to the 5th du. And now, well, that's a very nice antiderivative, right? So if I want to find the antiderivative of u to the 5th, I'm going to increase the power by 1, divide by the new power. So that's going to be 1/2 times u, times u to the 6th over 6 plus some constant c, or u to the 6th over 12 plus c. But now I have to remember that I'm not done. My original problem wasn't about u. I made up u to help me solve this problem. So at the end, I have to convert back to my original variable, which was x. And so I just remember that, well, u was sine of 2x. And so this is sine of 2x to the 6th power divided by 12 plus c. All right. So again, what we see here is we can do this method of U-substitution even when the thing that we're looking for we don't quite have the derivative that we're looking for here. But notice that this only worked because the thing that we had was almost the derivative. It's just a constant multiplied out front that was causing the problem. Okay. So in some cases, we can solve small problems with not having the entire derivative. All right, now it's time for you to practice one. So in this knowledge check, I want you to find the indefinite integral of the natural log of 3x quantity cubed divided by x dx. And before you get started, let me give you a slight hint to help you see this problem a little easier. Right? We're usually looking for some function and its derivative multiplied together. Think about rewriting this as natural log of 3x cubed times 1 over x. So take a moment, try to identify your u and your du dx, make the substitution, find the antiderivative, and then convert back to your original variable. Okay, great. Let's see how we solve this problem. So if I'm looking at this, I see natural log of something and I see 1 over x, and that might sort of prompt me, oh yeah, the derivative of natural log of x is 1 over x. What about the natural log of 3x? So if I had the natural log of 3x, its derivative, well, I need to apply a chain rule here, so that would be 1 over 3x times the derivative of the inside function. Well, the derivative of 3x is just 3. And so, in fact, the derivative of natural log of 3x is also 1 over x. So I do have a nice setup here for a u substitution. So if I make that substitution, I'm going to get the integral of, okay, my u is natural log of 3x, so it's going to be integral of u cubed times du dx. That'll be the same as the integral of u cubed du. And again, now this is just a power rule problem. So I'm going to increase the power by 1, divide by the new power, plus c. And then I just remember that I made up the u. I need to switch back to my original variable. So this is really natural log of 3x to the fourth divided by 4 plus c. And that is my final answer. Now, before we move on, a couple of words of caution. So far, I've sort of carefully curated problems for you where this works out nicely. But, well, Calculus 2 would be a very short course if every integral could be computed simply by applying the method of U-substitution. So we may want to know, when does this not work, right? What might it look like if this isn't going to work? Okay. So we have to be careful because very small changes in these sorts of problems can take you from something where U-substitution would have worked to something where it won't work. So take, for example, sort of these two problems, okay? Very similar. The only thing that's changed is the power on the x squared term, or sorry, on the x term sitting at the front, okay? In this case, I have x cubed natural log of x to the fourth. This can actually be done by U-substitution, which, by the way, we often call U-sub for short. Okay. However, this problem cannot be done by U-substitution. But let's just see, like maybe if you tried sort of some wrong things, what might happen, right? And what might be your sort of warning signs that things were going wrong. Okay. So let's say you thought, okay, I'm going to try this by U-substitution. Okay. So maybe you would say, okay, I'm going to let u be x to the fourth. And your first warning sign here would be, right, that this derivative is 4x cubed. Now, the fact that I have a constant here that doesn't appear up here, that's not such a big problem. I could take care of that. But here, the actual function part, the x cubed part, is different than what I have here. But maybe you said, well, I'll divide both sides here by 4x. So I'll get 1 over 4x du dx is equal to x squared. So now I can actually substitute in for my x squared here. And now when I do this, I'd get 1 over 4x du dx times natural log of u du, or sorry, natural log of u dx. And if I were to rewrite this, reorganize this a bit, so I get 1 over 4x ln of u du dx dx. And you might try to cancel those there, but you'll notice the problem is you haven't managed to eliminate all of the x terms here. So in this case, the fact that you, even after trying to do this U-substitution, you still have x terms left indicates that this is not a valid U-substitution. Okay. So while you can solve this integral by U-substitution, you can't solve this integral by U-substitution. Later on, we will talk about methods for dealing with such integrals, but U-substitution will not work here. Now, as I mentioned before, essentially indefinite integrals are equivalent to finding antiderivatives in a lot of ways, just asking it in a slightly different way. And so we might wonder then how this method ties to definite integrals. Okay, so when we're dealing with a definite integral, there are really two ways to handle U-substitutions, because again, U-substitution is a way of finding an antiderivative. So one is, you could just, if you have a definite integral, so you have limits of integration, right? Typically, the fundamental theorem of calculus, the way we would treat this is if I wanted to solve this, I would find an antiderivative and evaluate it at the endpoints and take a difference. Well, I could say I'm just going to use U-substitution to find this antiderivative function, and then I'll just directly apply the fundamental theorem of calculus. That's sort of option one. But there is a second option, which is I can actually do a U-substitution, and I can also transform the limits of integration during the substitution process so that I don't have to convert back to terms of my original variable. To see this, let's look at an example, and we'll actually complete this problem using both methods. All right. So let's say I was given the integral from 0 to pi over 4 of tangent cubed of theta divided by cosine squared of theta d theta. Now, as I stare at this, I sort of have two options. One is I don't immediately see jumping out at me a function and its derivative. So I probably need to do some sort of algebraic manipulation on the integrand itself before I'm ready to really apply U-substitution. So one thing I could do here is I could try to just convert everything to terms of sines and cosines. That would work. But that if I were to do that, well, tangent is sine over cosine. I'd end up with sine cubed of theta over cosine to the fifth of theta. I would then have to use some trig identities. It would just turn out to be very convoluted. Not a bad idea from a problem-solving sort of strategy point of view, but in the actual context of this problem, that's going to be very difficult. The other thing I could think is, okay, well, I see tangent there. I know the derivative of tangent is secant squared, and I have cosine squared in the denominator, but 1 over cosine is secant. So I can, in fact, rewrite this integrand just using the fact that 1 over cosine of theta is secant theta. I can rewrite this as the integral from 0 to pi over 4 of tangent cubed theta secant squared theta d theta. All right, that's making a horrible squeaking noise. And again, here I'm just using the fact that 1 over cosine theta is equal to secant theta. All right, so now doing that, I now see a tangent of theta and I see a secant squared of theta. So I do see a function and its derivative. So I'm going to try here the substitution, let u be tangent of theta and let du d theta be secant squared theta. So if I do that, my transformed integral becomes, well, sorry, let me pause for a second here. I'm looking at a definite integral, right? And this definite integral has limits of integration, and those limits of integration are in terms of x. So before I proceed with that definite integral, what I really want to think about is finding an antiderivative for this function. Okay, and so this is where I can use my U-substitution then on this indefinite integral. So this will become the integral of u cubed du d theta, or just the integral of u cubed du. Well, again, that's a fairly straightforward antiderivative. So increase the power by 1, divide by the new power, plus c. And so this is tangent of theta to the fourth divided by 4 plus c. All right. So now that I've found the indefinite integral, what I've really done is I've found all the possible antiderivatives. One way to evaluate this definite integral then is to use the fundamental theorem of calculus and come down here and just say, okay, well, what do I need? I need an antiderivative. So just set c to be 0 and take tangent of theta to the fourth divided by 4. And evaluate it at your endpoints and take a difference. So this would be tangent of pi over 4 to the fourth over 4 minus tangent of 0 to the fourth over 4. Okay. Now tangent of pi over 4 is just 1. So that becomes 1/4 minus tangent of 0 is 0. And so my final answer here is 1/4. So here, the U-substitution was just a strategy that I used to help me find the antiderivative. Then once I got everything back to theta, I plugged in my values of theta to get the correct answer. Okay. But as I alluded to, that's sort of option 1. There is a second option. Okay. And the second option is to convert your limits of integration at the same time you make your substitution. So going back here, at this step, instead of converting it to an indefinite integral to just find the antiderivative, I could have left this as a definite integral. But then when I made my substitution to u, I have to change my limits of integration from being in terms of theta to being in terms of u. And so how do I do that? Well, if theta is 0, then u would be tangent of 0, which is 0. If u is tangent of theta and theta is pi over 4, then u is tangent of pi over 4, which is 1. So in this case, this happens because u is equal to tangent of 0. And up here, we have u is equal to tangent of pi over 4, or 1. Right? And so I convert these limits of integration to be in terms of u at the same time that I'm converting the integrand to be in terms of u. And so now, this stays as a definite integral from 0 to 1. And now here, this is u to the 4th divided by 4, evaluated at 1 and 0 and take a difference, which is just 1 to the 4th over 4 minus 0 to the 4th over 4, which again gives you 1/4. Same answer, two different ways. It doesn't make a difference to me which of these you choose. So you can either use U-substitution to find the antiderivative and then go back and use the original limits of integration, or you can convert your limits of integration at the same time that you convert your integrand to be in terms of u. So here there's no need to convert back to the original variable because you transformed your limits of integration as well. So now I want to give you an opportunity to practice. So let's imagine you're asked to find the integral from 0 to 2 of x squared divided by the square root of x cubed plus 1 dx. So I'm going to pause and let you try to work out this problem. Okay. In this case, I'm actually going to employ the second method. I'm going to convert the limits of integration at the same time I do my U-substitution. So here, in order to do my U-substitution, I first need to identify a function. So in this case, I'm going to use x cubed plus 1 and its derivative, which would just be 3x squared. Now you might be saying, I don't see a 3x squared sitting up here. I just see an x squared. So I may need to use the fact that I could rewrite this in this way. Okay. So now, making my substitution, this integral from 0 to 2 of x squared over over square root of x cubed plus 1 dx. When I convert everything to be in terms of u, a couple things are going to happen. So my x squared is going to become 1/3 du dx. This is going to become square root of u in the denominator. And now I'm also going to convert my limits of integration, right? So when x is 0, u should be 1. Okay. And when x is 2, u should be 9. And so now here I get this is the integral from 1 to 9 of, I can pull this constant 1/3 out. And this would be u to the negative 1/2 du. Now, applying my power rule here, I'm going to increase the power by 1. So adding 1 to negative 1/2 gives me positive 1/2. I'm going to divide by the new power. That's all going to be times 1/3 plus, And then here, since I've converted my limits of integration, this is going to be evaluated at 9 and 1 and take a difference. First, let me clean up this antiderivative piece here. So this is going to be 2 square root of u over 3, evaluated at 9 and 1 and take a difference. So if I evaluate this at 9, if I plug in 9 here, I'll get 2 square root 9 over 3 minus 2 square root 1 over 3. So this will be 3, which will cancel there. So I'll get 2 minus 2/3. And if I convert that, 2 is 6/3. So this final answer is 4/3. So it's a little down in the corner. So let me just pull it back up here. So this should give me, this is equal to 4/3 is my final answer there. Okay. Again, you don't have to convert the limits of integration along the way. You could have done it the other way where you just use U-substitution to find the antiderivative, but I just thought we'd practice this method as well. All right. The final thing I want you to see, although I won't ask you to do many of these, is that substitution is actually a really powerful tool that can be used in lots of even subtler ways than the ways we've looked at. So so far we've really looked at ways where what we're seeing in the integrand is a function and almost its derivative sitting there. But there are other cases where you can use sort of more complicated notions of substitution or trickier notions of substitution. So for example, in this problem, so if you were to see this, it'd be a little tricky to figure out exactly what the antiderivative of this was. But I can do something that's a little sneaky here. So imagine that I set u to be equal to y plus 1, okay? Then my du dx, or sorry, du dy in this case, is just 1, right? The derivative of that is just 1. And, well, I always have a 1 sitting around, right? So I could take this integral. I could just say I'm multiplying by 1 there because that doesn't change the value. Okay. And now I could start doing the substitution. Now, it's clear that this part would become square root of u. I get a du dx, sorry, du dy here. But I have this y term here I need to take into account. And well, if I looked at this, I could say, well, this is u minus 1 is equal to y. So what if I put this here? Oh, sorry. I really just want to plug in here u minus 1. Okay. And so what I end up with is u minus 1 times the square root of u du. And this is now much nicer because if I think of this square root of u as being a u to the 1/2, then I can distribute this and I get the integral of u to the 3/2 minus u to the 1/2 du. And so just quickly applying the power rule, I get 2u to the 5/2 over 5 minus 2u to the 3/2 over 3 plus c. And then at the end, I would just need to plug back in what my u was. My u was y plus 1. And so for my final answer, I get 2 times y plus 1 to the 5/2 divided by 5 plus minus 2 times y plus 1 to the 3/2 divided by 3 plus c. Yeah. Again, this one's a little trickier to see because when I look at this integrand, I don't really see a function and its derivative, not in the same way that we saw it in the other problems, but I can still actually take advantage of the notion or the idea of substitution to help me simplify this integral, right? So instead of dealing with this, I was now dealing with this, and that was nicer because I could I could just distribute here where I couldn't distribute this easily here. I could now distribute here and then find the antiderivative sort of just by using the power rule. So we'll stop there for substitutions. You're going to have both homework and quiz problems on this method of substitution. I encourage you to, in some sense, embrace the struggle. Early on, it will be difficult to maybe quickly see functions and their derivatives, but keep working. I'm available for office hours, so come see me if you find yourself getting really stuck or really frustrated. I'm always happy to talk and help you work through those problems, but you'll now have a number of problems to practice on your own to help you master the method of U-substitution.